Gabriela Jeronimo from University of Buenos Aires, and she will speak on a beautiful new result on it's a new bound on differential Nullstellensatz.
Thank you. First, I'd like to thank the organizers for inviting me. It's a pleasure for me to be here at the coaching seminar and give this talk. And well, as he told, I'm going to speak about the result containing a joint work with Lizy D'Alfonso and Pablo Soberno about the bounds for the differential Nullstellensatz. So I'll start telling you what the problem is. First, the classical Hilbert's Nullstellensatz, which deals with algebraic polynomial systems. It states that if we have a system of polynomials f1, fs in n variables x1, xn with coefficients in a field k, then the polynomials do not have a common solution over the algebraic closure of k if and only if the ideal generated by the polynomials is the whole polynomial ring in the variable set. That is, this is the same as saying that the polynomial 1 can be written as an element of this ideal, that is, as a combination, linear combination of the input polynomials with coefficients which are polynomials. These pi's are polynomials. So this is a classical result in the algebraic setting, which was later extended to the differential setting by Reed. Here I am going to present the statement in the setting of ordinary differential fields, but it also holds for partial differential fields, but as our work is in the ordinary setting, so I'm focusing on that. So we have here a field which is now an ordinary differential field, and differential indeterminates, and now differential polynomials with coefficients in this field. So the statement is that the system of differential equations given by those polynomial cells has no solution in any differential extension of k if and only if now the differential ideal generated by the polynomials equals the whole ring of differential polynomials in the variables x. Here, this is the ideal generated by the polynomials and all their derivatives. Now, saying that this ideal is the whole differential polynomial ring is the same as before, as saying that the polynomial 1 can be written as a linear combination of some of the derivatives of the input equations with coefficients that are differential polynomials in this ring. So, but this is now a finite linear combination, so only finitely many derivatives are involved here. So we focus on effectivity results on the differential Nullstellensatz, but first I will introduce the effective Nullstellensatz in the algebraic case, which is the following task. Is to find an a priori upper bound for the degrees of the polynomials that give the linear combination producing 1. So the problem is, given the fi's that do not have a common solution, and in terms of the number of variables, the maximum degree of the polynomials, what one wants to do is to get an upper bound for the degrees of these pi's. The best known bounds are due to Kolar and then to Jelonek, and it is d to the n, where, as I said before, d is the maximum of the degree of the polynomials and n is the number of variables. So why are important this? Why a kind of result like this is important? Because once I have a bound like that, I can translate this to a decision procedure. So if I am given now f1, fn, polynomials, and I know the bound for their degrees, so I do not know if these polynomials have a common solution or not, but if they do not have a common solution if and only if there are some polynomials pi satisfying that identity. So what I can do is to say, well, this polynomials pi will be a certain combination of monomials when these exponents alpha will be just alpha 1 alpha n. But no, not any monomial, but monomials of degrees bounded by d to the n, that is the sum of the coordinates alpha is bounded by d to the n. So I put here coefficient variables, a new variable for each possible coefficient. I now construct the sum which will be a polynomial with coefficients which will be linear combinations of the coefficients of the I times these variables which are here. So when I equate this to 1, I get a linear system with finitely many equations because I know which are the equations. Each possible coefficient of each monomial of degree bounded by the sum of the degree equal to 0. So I have a finitely many equations where the knowns are these ones. So if the system is consistent, so I know that the polynomial 1 can be written as a linear combination, and so the original system does not have a solution. And if the system is inconsistent, it's because the original system has a solution. So this is the importance of this result because it gives an effective way to test whether the system has a solution or not. So one wants a similar thing in the differential setting, but now it is not only the degrees what cares, also the order of the derivations, because the first thing I do not know is, how many derivatives do I have to compute here to make the linear combination. So the main thing to determine here is this number L appearing in the identity. And one wants a bound for this cell in terms of the same kind of parameters, the number of variables, the degrees of the polynomials, and the order, the maximum order of the input differential polynomials. In the partial differential case, of course, the number of derivations could also appear in the bound. Once one knows this number L, the degree bounds follows by using the result of the algebraic setting, because now we are in finitely many polynomials in finitely many variables, so it's an algebraic situation like the previous one. So the important thing to get the whole effectivity aspect is to get the order bound, because order bound plus the effective classical Nullstellensatz produces the degree bound. Well, so this problem, the differential Nullstellensatz, has a long history since Ritz, and there is a first constructive proof by Kohn, among others. Then, a proof of Seidenberg, which shows the existence of an order bound, but there is no explicit bound. And then there is a recent work by Triple, which gives the first explicit order bound with full generality for the differential Nullstellensatz. So full generality, it is not only for the ordinary case, which is what I am going to explain now, but also for partial differential case.
Can you ask you a little bit about the constructive proof? Isn't it true that in this paper, which is I think his first paper, he passed away a couple of weeks ago, that he shows constructively how to take one and write the expression, actually find the coefficient polynomial.
I don't know if I understood the proof.
No, the thing is that if you are able to actually compute that expression one into
don't know.
that.
I don't know. Me particularly, I don't know. But I don't know if another person could understand and translate it into...
I think the constructive proof is assuming that the system has no solution.
Yes, it's possible.
Then he could write down one.
Yes, it's possible.
He's doing a constructive.
I don't remember now the details, so I cannot tell you more than that.
But then the bounds should be.
Huh?
But then the bounds would be known.
No. He's assuming. See, the thing is, with the bound, you don't know whether the system is solvable. Whereas Kohn assumes that the system is not, and then he proceeds to do it. He knows that. And he has a little bit more knowledge.
But here,
to produce
a
that.
priori
But
bound
here,
is
you don't
yeah.
know.
Yeah.
So therefore, you need a bound to actually make you know. But once you know that, actually this is still assuming the same thing, isn't it?
Yes, that's not the problem to assume
I
that.
think we should look more carefully at Kohn's paper again.
Yes, maybe.
Yeah.
But,
I think the point is that
I mean, he may
it's
not be give
confined
a
to-
bound, but he actually computes, give you an algorithm to compute that expression.
It's only from
something,
neuromorphic.
William, bound is something uniform, so it's not for a particular system. So
No.
it's,
Well, but what's the use of bound if you're not looking on a particular system afterwards?
well, that's how you apply it.
Right, exactly.
Yeah, so it tells you, in a sense, how many steps your rewriting will be. You see, the bound tells you how many steps you have to go. If you just have an algorithm
Yeah.
with the rewriting, you
Well,
don't know how many steps it's going
Yeah.
to make and how far you
That's
have to go
true.
to do it.
it's
But
not
it's-
exactly the same to have a bound that you have a procedure.
There's a
Oh, you
forecast.
still know it
Bound is a
ends.
forecast.
You still know it ends.
But if this,
You know that it ends, but you don't know.
Yeah, but if you don't know how long will it take, you don't have a bound. That's the problem. And I think that's the basic problem in the whole differential algebra thing, because most of the time one has procedures that eventually
Ends, right?
end, but you don't know how many times, and you can notice, or the estimations are hard to get. Yes. So here is our main result, which is, as I told you before, a bound for the number of derivatives of the input equations necessary to write the polynomial 1 as a linear combination of ds and those derivatives. The bound is this number here, is n times e times d, which is the number of variables, the order, the degree, power to the 2 to a constant times n times e to the third power. Here is an unknown constant that one could estimate, but it's not very nice to make that estimation. So it's a double exponential bound, which leads to a triply exponential decision procedure then. So I made a statement here for the field of complex numbers, but in fact it holds over an arbitrary field of constants, and also one can extend it to a field of rational functions in one variable, adding the condition that t prime equals 1. So adding one equation, one can extend it a little bit further.
so that's also for positive characteristics.
No, it's characteristic 0. No, the whole thing is characteristic 0.
C, sorry.
C, then you can extend it to a field of constants but of characteristic 0, or functions in rational functions in one variable with the coefficients in a field of constants characteristic 0.
That's is like.
So double exponential And as I told you before, it gives a decision procedure for consistency of the differential system with a triply exponential running time, because now one has to add one further, I will explain it later, one power more to write things down. So a previous algorithm for quantifier elimination was due to Grigoriev, and in this situation it has a complexity of the similar hierarchy, triply exponential.
I have a question.
Yes.
So, other counterexamples to this bound
As best possible.
in partial cases, in the case of several derivations, and in cases of fields that are not C, C of X, and so on. So in those cases that you have not...
No, we don't have nothing.
Nothing.
No, we don't know. No, we don't have any counterexamples nor proofs. Nothing.
So, naive question, what's the complexity known if you just compute the characteristic set and check whether one is in the characteristic set?
I don't know which is the complexity of computing a characteristic set. I think it's more similar to the previous one, the previous bound.
Because pragmatically, of course,
I think the bounds you get via characteristic sets is more like the one here. But
there's still an upper bound, so
yes.
no one knows. There is
No.
no good bounds yet.
That's the problem. We don't have good bounds for characteristic set complexity.
They might exist, but we just don't know them.
Yes.
In the Grömer basis space, there are explicit bounds.
Yes.
Just
I don't know how they compare with the effect.
We use here in the middle complexities of Grömer basis, and these are doubly exponential.
Right.
And that's why we got doubly exponential bounds. Yes. So the general approach is to consider, we consider first systems of this type, which is first order. Here are a number of variables x and a number of algebraic constraints g. So we have n variables x, n variables u, so n polynomials s and s polynomial g. And we find the bound first in this setting. Then, for an arbitrary system, it is easy to transform it in a system like this by renaming the variables. So now we will have more variables, but a first order system like this one, making this a change of variables that is here. So the first derivatives we know, we call them x1, the second x2, and so on. And if the order is E, the last ones are the U variables appearing here.
So are the F's and G's differential polynomials or regular polynomials?
Are differential polynomials, but in fact here are regular polynomials because they are order 0. But we consider as differential polynomials because we differentiate them.
Excuse me, but when you say given an arbitrary DAE system, that really means an arbitrary collection of differential polynomials.
Yes,
right?
if a list of polynomials of any orders with the maximum order E, so if the maximum order is E, we transform it in n times E variables, making this change here.
So, could you explain your so you split variables into x and u? So how do you split?
X are those, you have an explicit part of the system, x dot equals something, and other equations that do not have any derivatives. So the ones that are derivative, those are the x, and the remaining ones are the u. So here is the first particular case we consider, which is the case when this part defines finitely many points. the equations G equals to 0 defines a zero-dimensional variety of these finitely many points. This case is very easy because it's like the case in only one variable. Now I will do the computation here. So if the system has no solution, it is necessarily these things will be empty because we have a common zero of the S and the G with plug in here, and we got the solution to this system. The constant x equals to x0 and u equals to u0. If u0 is a point here, will give us a solution to this system. So the first thing is that the variety defined by all these polynomials is empty. This holds always in this situation or in the general situation. But if you have this, then by the classical algebraic Nullstellensatz, the polynomial 1 is a linear combination of the f and the g. Making this rewriting here, it follows that 1 is a combination of x dot minus f, g, and x dot. So if we can write x dot as a combination of these polynomials and some of their derivatives, we are done. So in the zero-dimensional and radical ideal situation, so not only asking that this is finitely many points, but also that the algebraic ideal is radical, we have that for each variable there is a polynomial in this single variable which is in the ideal. This is a consequence of being zero-dimensional, and the polynomial Pj will be square-free if the ideal is radical. So if the ideal is radical, we have this polynomial. So this polynomial is square-free, so it has no common solution with its derivative. So these two polynomials in one variable now do not have a common root, so they are relatively prime. The one can be written as a combination of them. Multiplying by xj dot, we have this equality here, but now the polynomial which appears here is the total derivative of the polynomial pj. So we have that the variable xj dot is a combination of the polynomial pj and the first derivative of the polynomial pj. And so it lies in the ideal generated by g and the first derivative of g, because p was here, so when I differentiate, it will be a combination of this and these ones and their derivatives. So this computation which is here is the thing in the one variable. I do it for every variable, and then I come back here and get that the polynomial 1 is a combination of x dot minus s, the g's, and the first derivatives of the polynomial g. If the ideal is not radical, what we are going to do is to change the polynomial g by the generators of the radical ideal of the variety defined by this system. In fact, one could do the same thing here, but it is not true that 1 is a combination of pj and pj prime, because pj is no longer square-free if this ideal is not radical. But one can take more derivatives in order that they do not share a common solution and make a similar computation, longer but similar. But in any case, we didn't want to do that, so what we did was to replace the original polynomials j by new polynomials defining the same variety by generating the radical ideal. So in the general case, we will have here constraints which define an algebraic variety, but now of an arbitrary dimension. So the idea of the proof is to change this system, the original system, recursively by changing the algebraic constraints. And at each step, we add new constraints in order that the dimension of the set of constraints decreases. At some point, we will have an empty variety of constraints that we will have inconsistencies, or we will have a finite set, which was the previous one, the previous case. And then, when we finally get finitely many points or an empty set of constraints, we can write the polynomial 1 if the set of constraints is empty because of the classical Nullstellensatz of the algebraic setting. And if the dimension is 0 and the ideal is radical, it's as in the previous slide. But now we have the one written with the new polynomials, which are not the original polynomials here, are the GR of the corresponding step. So the next part is to make a listing procedure going all the way around. That's it. From the writing of the one in terms of the polynomials GR, we will go up until the original polynomials J. In doing this listing, the number of derivatives will be increasing at each step, at each listing step. So now I will try to explain you the first part, the decreasing dimensions, and the listing step. In order to decrease the dimension of the algebraic constraints, what we do is a prolongation and projection. It's a classical tool in this context. So we consider the algebraic constraints, we differentiate them, and we got new constraints J tilde by replacing x dot by the polynomial s according to the first equations, and leaving the rest of the equations unchanged. So now we have new polynomials which are equivalent to the first derivatives of the chase modulo this ideal. So these polynomials lie in the ideal generated by x dot minus s and the j dot. Now we consider the zero set of the polynomials, the original ones, and we add these new ones here. But these new polynomials depend not only on the variables x and u, but also on the derivatives of the u's. So here we have an algebraic variety in a bigger space. This is the part, let's say, of the prolongation. Now we project to the xu, to go back to the original ambient space. And so the result, which enables to ensure that with this procedure the dimension of the algebraic constraint decreases, is this lemma that I state here, is that if the system here is inconsistent and the ideal is radical, when we make all this computation, that is prolongation, projection, and we compare both varieties, the projection of this one with the original one, the new one, the projection, is strictly smaller than the original one. In fact, all the reducible components of the variety are strictly smaller than the previous one. So, no irreducible component is contained here, so it will get smaller, and in particular the bigger components will get smaller, and the dimension of the variety will be smaller than the previous one. So, starting with an arbitrary system with no solutions, the first step is to change the algebraic constraints by polynomials not defining, generating the radical ideal. If this is zero-dimensional, we are done. If not, we consider the prolongation and projection, which algebraically is to consider this ideal generated by G0 and the prolongations. Intersecting here is like making the projection, and we compute the radical ideal and take a generating system G1. So now we have a new system, sigma 1, which is still inconsistent because we have the constraints which make them inconsistent, but now the algebraic constraints are smaller, and the ideal is radical. The important part is that the algebraic constraints are a smaller set. So we repeat this a number of times until we get to a zero-dimensional situation or an empty set. Then the recursion ends. We have that we have to make at most as many steps as the dimension of the original variety, because at each step we are sure that the dimension decreases at least by 1. So no longer than n plus m steps are needed. And at each step, summarizing, what we do is to get a new system of polynomials which generates the radical ideal of the prolongation projection of the previous one. In order to estimate the number and the degrees of these polynomials, we get this boundarized right here. What we do is to use a couple of results of the algebraic setting that I will recall now. One is that from Grabner basis, and it has to do with the generators of the radical. If you have an idea generated by polynomials F1 and S with degrees bounded by D and variables, then the radical of B can be generated by S times B, S B to be O constant times nu times n, where this is the dimension of the zero set of this one, or 1 if this is zero dimensional. This is a bound for the number of generators and the degree of the generator, and this bound follows from Grabner basis analysis. And this is, in fact, this is the second one we need. The first one we need is for generators of the intersection of an ideal. So there we have an intersection of an ideal in variables x, 1, u, and u dot, and we intersect this one. This corresponds to projection, and here the result we use is that the degree of the generators can be taken to be bounded by the degree of the zero set, the degree of the variety defined by this projection. The generator is bounded by the degree of the variety defined by the ideal, and in order to bound the degree of the variety, we use the Besut bound, which is the product of the degrees of the generator. In fact, a refined version of the Besut bound is what we use. So, by using those results from commutative algebra, from effective commutative algebra, we get this bound here, which is, let's say, the base of our next bounds. So this is the prolongation projection step. We have that the polynomial 1 is a combination of the polynomials at the last step and the first derivative. This is because of the zero-dimensional case. And now we have to go back to the original system of differential polynomials. So at each step of the previous recursion, we have a system which is inconsistent. So we have that the polynomial 1 is in the differential ideal generated by all the equations forming the system. So there is some number, which we do not know a priori, of derivatives of the original equations, x times x dot minus f, and the ones we added. This notation is these ones and all their derivatives up to order k. And so the polynomial 1 will be in that algebraic ideal. On the other hand, we know that there is sorry, I have to recall something because that in order you to be able to follow that, we have that the GI were in the radical idea of this one. In fact, it was a radical intersection with a smaller ring, but in particular, they were in the radical idea. And so what I'm saying there is, if this is in the radical idea, there is some power which is in the ideal. That's just the definition of the radical ideal. But in fact, there is a power which serves for all of them, and that can be estimated in terms of the degrees of the generators of the ideal. The result is that if the generators have degrees d and n variables, the exponent is like d to the n. The degrees to the number of variables. One can estimate this number, but the important thing is that there is one exponent here which serves for all polynomials in the radical ideal, and that we can estimate it. So this is the epsilon I here, this is the netter exponent of this ideal. And for the original one, recall here there was no projection, it was just taking the radical of the given algebraic constraints. These were the G0. So what we prove is that if the polynomial 1 can be written with k derivatives of these ones, then it can be written with 1 plus this number times k derivatives of the previous ones. And a similar thing, but with the original one. But no one appears and does not make any difference. So the number of derivatives needed at each step multiplies by the netter exponent of the corresponding ideals. So recursively, what we have is that for the original polynomials, we will have to use at most n plus m times the product of all these exponents needed here. Well, so this is what the bound I told you before, that we have a bound in terms of the generator for the netter exponent of the ideal. So for the first one, we have d to the n plus m, and at each intermediate state, we will have something like this, because the generators have degrees of this order. So multiplying all these things, we get something like this, because these numbers are bounded by n plus m. And so this is the final bound for this particular case, which is not particular because any system can be transformed into something like this. So it is the double exponential bound depending on a constant here, which comes from the Grebner basis estimate of the degrees of the generators of the radical ideal. So the general case, the system is transforming something like this. Here it should say G, but I don't know why I put S, but this will be like the polynomials G before, no S. And we get a similar thing. Now we have n times e plus n variables, which is this thing like things appearing here. And for the degree bounds, we have we use the classical algebraic Nullstellensatz. So now we have that if the one is in the polynomial ideal, in the differential polynomial ideal, then it is in the algebraic polynomial ideal generated by the first L derivatives with L of this type. So using the bounds from Jelinek for the classical Nullstellensatz, we know that the one will be a linear combination with polynomials of degrees bounded like this, with this n is the number of variables appearing here, which is at the beginning there were derivatives of order almost e. Now we differentiate L times, so now we have e plus L sets of the plus 1, e plus L plus 1 sets of n variables each. So this number is the total number of variables. So this is the one appearing here. And then we have a linear algebra-based algorithm to decide consistence of the system of arbitrary order, which will be triply exponential complexity. The algorithm is the same as I explained you before in the algebraic case, but we have to take into account all the derivatives of the polynomials, and again we put algebraic indeterminate coefficients for this pi and make the equations for the coefficients here. Well, the last thing is that we can get also bounds for the strong differential Nullstellensatz. The strong differential Nullstellensatz is now for an arbitrary system which may have solutions. So we now have S, which is a system of S differential polynomials, and an additional polynomial. And the information is that every solution of the system is also a solution of G equal to 0. Under this assumption, the strong Nullstellensatz says that the polynomial G, this one, will be in the radical differential ideal generated by the polynomials F. This is the differential counterpart of the strong algebraic Nullstellensatz. So there will be some power of G that will be in the ideal generated by a finite number of derivatives of the polynomial F, and we can estimate the power and the number of derivatives like this. There are similar bounds as in the previous case, and the proof of this follows from the previous differential Nullstellensatz bounds. First, by using the Rabinovich trick. This is a standard result from algebraic geometry or commutative algebra. Let's say that if we can take a new variable and add this equation. But now this system has no solution because the assumption was that each time that all the polynomials vanish, the polynomial tree also vanishes. So this cannot be 1. There is no possible y, so that this is 1. So for each solution here, it is not a solution of this equation, so the complete system has no solutions. Then we apply to this system the previous weak Nullstellensatz for the differential case, and we get that the polynomial 1 is a combination of the derivatives up to order of this type. So now think of the equation 1 written as a combination of these guys, and substitute each time that appears a derivative of the variable y, substitute it by the corresponding derivative of 1 over 3. By doing that, it follows that a tree lies in the radical ideal generated by the L derivatives of the polynomial cells, the same L as before. And finally, using the strong classical Nullstellensatz, now we are in the situation that we know that G is in the algebraic ideal generated by these many derivatives of the F. What we are missing is the power m necessary for it to be a linear combination, but now we are in a classical algebraic setting, and we know from the paper I mentioned by Jeronimo that this power m is just due to the number of variables, which is this one here. So this short proof shows that this bound follows from the previous one for the inconsistent case. Well, and now we are trying to adapt all this to the partial differential case, but it's a whole different story. This is much more difficult to deal with that case. For the moment, we are able to deal with systems of this form, which is similar to the semi-explicit systems I deal with in the ordinary case at the beginning. So now we have here n independent variables, m independent variables and n differential unknowns. So we are thinking that we have a differentiation with respect to m different variables, and the system is like this. We know all possible derivatives of all the variables with respect to all the independent variables. Under these assumptions, and in this particular situation, we think that the same technique can be applied, and that the same kind of triply exponential bound is attained.
And how far is it from the most general form?
It's far, very far. Because the problem is that here I am assuming that I have something for each possible derivative. That is, if you have let's say there are two variables, y1 and y2. Maybe you have a derivative with respect to x1 and x2. So we assume we have all these equations.
Oh, just a second, and u is y?
Yeah.
U is y.
No.
U is y, sorry. Yes, U is y. Here is xy. Yes, that was a typo. So, we assume that we have all this information in the system, and then maybe algebraic constraint. But we do not know what to do if some of those are missing. Yeah, we don't know how to deal the situation if some of those are missing, which is not the same as saying that they are zero here. They are not appear.
They don't appear.
They don't appear at all. So we cannot treat yet. We don't know how to treat that case when some of the derivatives are not given.
But also, not every partial system can be put into this form.
No, but in any case,
Right.
yes. No, and if you have an arbitrary partial system, and we try to,
That's right.
the situation appears when some of the derivatives are not present, and so you don't have the information.
Do you consider transformations of both the dependent and the independent variables?
We consider transformations,
As a part of general systems. So
and I
transformation
think
don't-
that making some kind of transformation, we could achieve the case where some. I think that we could, by making transformation, get to the situation that some specific ones do not appear. But we are working on that, but it's just a very working,
Oh, yes, you can.
very recent work.
You can do that by you can do that to homogenize the equation in some sense, and also homogenize the derivations. Then in that case, then they will be much denser, and probably you can find these constant matrices that will transform it so that every one of them will appear.
Yeah, okay.
If
We could try, yes, and your idea is good
But
too.
the differential type, the
That's
differential
right,
dimension is
exactly.
invariant.
That's what I'm
Then
thinking about.
you transform also the derivations,
That's
which
right.
corresponds to the independent variable,
Yes.
linearly.
Linear.
Yeah. But yeah,
I'm not sure about it.
it's just, this is just very recent, and we haven't.
Whether you can reduce it to first order, that's a different problem.
Yeah.
That's the big problem.
So-
That's not like in the OD case.
Right, it's not like the ODE case.
So this is what the most we could do up to now is to deal with this case of when all the derivatives are given, and we are trying to deal with the case when some of them are not, by making changes of variables as he suggested. But for now we are working yet. We are in the middle of our work, and this is.
Maybe you can change the
Oh.
first order.
Thank you.
Do the same, maybe do the same thing. Yeah, you should be able to do the same thing.
So could you comment on sharpness of your
You
model?
can change
Sorry?
the order.
On the sharpness.
Whether you can solve
On the
it.
sharpness,
It's not linear.
we have some example. The same classical example shows. I don't remember now. It's not. We cannot prove that it's sharp. No. In general, no. Let me recall. For some particular case, yes, in our work we included some examples showing in some particular cases sharp, but not with full generality and variables and so on. No, we don't have a family of examples showing that the bound is sharp. We couldn't find, so we do not know. And in fact, the bounds we use on Gremner basis, I think those are not known. I don't know, because the polynomials that appear here are not any polynomials. They come from differentiation of previous one. It's kind of difficult. Yes, we don't know.
But you have an example.
We have an example,
where the
but
bound is hit, right?
we have an example where the bound is attained, but
This is
a
one.
particular example, not the family of examples. Just one variable x and many variables u, but it's particular because it's one.
is a big improvement
Thank you.
from the Ackermann function.
Thank you.
At the end, we don't need differential algebra. We just do polynomial algebra.
So that concludes our
Yeah, that's good. The day, and we resume tomorrow morning at what? 9 o'clock, is that right?
Different room though, right?
Different room.
Different room, let me check.